In section 5.4 part 2, we're going to look at conditional probability. Conditional probability means that a condition has been specified. Some information is already available and we must use that information in the calculation. So our notation will look like this. The probability of event B occurring given that, that's how we read that line, it's straight up and down, it's not slanted. Probability of event B occurring given that this condition is that we have this condition A has already occurred. That's how that's read. The probability of event B occurring given that we already know that A has occurred. So let's write that in words. The probability of event B given that event A has already occurred. So remember, we've talked about single trial and then multi-stage experiments or procedures. In this case, this has to be a multi-stage procedure because something has happened already. So more than one occurrence of something has happened. So we might just remind ourselves by putting in parentheses down here, multi-stage procedure. That's what this has to be. It can't be a single trial because you've already had something occur. Okay, so remember way back we had an example of a spinner and then roll the die, and we said that was the first multi-stage procedure we saw. So perhaps it would be the probability of rolling a 3 given that when you spun the spinner you got a red or something like that. Okay. From section 5.3 we learned that many multi-stage, more than one trial, experiments can be done in two ways. We learned the two ways are with replacement and without replacement. And we said that we need to consider whether or not, that leads us to the decision of whether or not we have independent events or dependent events. So do you remember with replacement, would that be independent events or dependent events? So remember, with replacement would be like you put the ball back in the urn before you draw a new one out. So you're starting over from the beginning every time. So that one would be independent events. The events are independent of each other because each time you've got the same setup that you had the first time because you keep putting everything back in place before you do the next thing. But if you don't put everything back in place, now you're making all these different events dependent. Remember it now, put events. Now, in the example of the balls in the urn, if you don't put a purple one back after you've pulled it out, then now the next event is dependent on the fact that there's one less purple ball in there, right? So that's going to affect the probability of purples, and it's going to affect all probabilities because the denominator's changed. The total number is now one less. Okay. So which of these two ways includes a condition we must consider? Do you think it's with replacement or without replacement? Has a condition that we have to consider? Obviously, it's without replacement. We have to consider, as I was saying, you have to think about, okay, we took up one of the balls out of the urn, so we've got to consider that condition. But if you keep putting it back, you don't have to think about anything, right? So without replacement. Okay, we have an example here. Compute conditional probabilities. A jar contains 10 white jelly beans, 20 green jelly beans, and 80 pink jelly beans. Well, by now we know in order to do probabilities, we need to know how many jelly beans we have. So let's add that up. We've got 10 plus 20 plus 80, and we get 110 total jelly beans. We're going to need that number, right? If 5 jelly beans are selected, and this is one at a time, you're not just reaching and grabbing 5 in one swoop. 5 jelly beans are selected with replacement. So you pull out a jelly bean, you note the color, you throw it back in. Okay? With replacement, find the probability that all 5 are pink. So we want the probability of, and I'm going to use a P to represent the color pink. The first one's pink, and the second one's pink, and the third one's pink, and the fourth one's pink, and the fifth one is pink. Okay, so with replacement means every time we pulled one out, we had the same setup that we had on the very first one. So the probability that the first one would be pink, well, we said there's 80 pink out of 110, so it's 80 out of 110, right? And this is the multiplication rule because it's a multi-stage experiment, and we have the word and. So we're going to multiply that by, well, we put the pink jelly bean back, and now we're reaching again. So there's still 80 pinks, and there's still 110. And we're going to do that 3 more times. Right? Well, maybe you're already thinking, there's a better way to write that. And there is. We can use exponents and say 80 over 110 to the 5th power. And it's handy because we can use our calculator now to calculate that. The best way to do that is to type in the parentheses. There is a parentheses on your calculator. The open parentheses, 80 divided by 110, close those parentheses, and raise to the 5th power. And you should get 0.2034, or rounded to, we'll round to 3 decimal places, 0.203. Okay, let's compare that with what would happen if we do the same procedure, but each time we pull out a jelly bean, we get to eat it. So we're not putting it back. Okay, it looks the same as we write it out. You can't tell from the way I write it out whether I did it with or without replacement. That has to be somewhere in the wording here. So first one, second one, third one, fourth one, fifth one are all pink. But now look what happens. When we reach in there for that first one, there are 80 pinks and 110 jelly beans. But I can't raise it to the 5th power because now there are only 79 pinks and 109 jelly beans. And now I've eaten those two. I reach in again. There are only 78 pinks and 108 jelly beans, and so on. 77 and 107 and 76 and 106. So we've got to get our calculator out for that one, right? And run through that on your calculator and you get 0.1964, or about 0.196. So you see we did not get the same answer. It does make a difference. There's a condition here. One of the jelly beans on each trial is being removed. So obviously with replacement is much more efficient to calculate than without replacement. And therefore they have something called the 5% guideline for cumbersome calculations. Would you agree with me that this is a bit cumbersome? Yes. And what if it were 10 jelly beans? What a pain, right? So what this guideline tells us is if the sample size, the number that your sample, in this case it was 5, if the sample size is no more than 5% of the population size, we can just treat the events as independent. What was independent? Back up here, with replacement. We can treat events as independent. Now these words sample size, population size, we'll be talking about that some more in chapter 1, but we can pretty much from context you can see what I'm talking about, what we're talking about here. Our sample was 5 jelly beans. Our population was 110 jelly beans. And we often use a little a small case N to represent our sample size and an uppercase N to represent our population size. So the math way to say this is if your sample size is less than or equal to 5% written as a decimal is 0.05 times your population size. You don't really have to memorize that, but we just want to be able to do this. So let's see, in our example, is 5 less than or equal to 0.05 times 110? Let's check our example. Is 5 less than or equal to, when you multiply that out, you get 5.5? Yes. So that means in this case, it would have been acceptable, since the sample size is no more than 5% of the population size, it would have been acceptable for us to do the easy calculation rather than the cumbersome calculation here. Okay, let's look at this last little example on this page. All right. If 9 students are selected without replacement from a population of 165 students, can we treat these events as independent for easier calculations? So, sample of 9 students, population of 165 students. So the question is N less than or equal to 0.05 times 165? So 0.05 times 165 is 8.25. So 9 less than or equal to 8.25? No, it is not. So in that case, we don't have to work the problem, luckily, but they just wanted us to practice this. In that case, we would not be able to assume or pretend or whatever you want to call it or treat these events as independent. That population is just too small for that. If they could have more students in their population with 9 out of a larger number, it's getting pretty close, then they could. But in this case, they can't.